a lot in the last lecture. The quantum, so it's not quantum, but we can say that nano devices are being formed using these materials. So the first example of this nanomaterial, I take plasmonic noble nanoparticles, noble metal nanoparticles. You have seen in the periodic table a group called noble metals. These metals you all know when it is in bulk form, gold, silver. But some of the properties, like they can absorb even a single photon of light. This behavior comes at this scale. With the size of these particles are coincident with the size of wavelength of the light. There is an absorption of the light, and this is very unique property that can be used in different way for different applications. So the two main points are the selective photon absorption, means it can select, it can absorb even a particle wavelength, and localized electric field. So these two properties normally modified in different way for different applications. When these metals are combined with semiconductors or different other materials, they also enhance their properties because of this unique, that is called SPR, surface plasmon resonance property, where it can enhance the electric field around this and also the absorption of light. One of the example, just to say that one of the properties, whether it can absorb light and provide some heating that can kill the cancerous cells. So these materials are not only like optical material, but they can be used for health purpose also in biomedical field. This is just an example to show, and there are different multifunctional applications of such kind of materials, especially the noble metal nanoparticles, which are called plasmonic particles. So I'm talking about one of the features that is called surface enhanced Raman scattering. Everybody knows Raman spectrophotometer. You study in your graduation, post-graduation about Raman effect. Using that concept, these materials are highly selective and very important. Using this concept of Raman effect, it can be used for sensing very small amount of material. Even a single molecule can be detected. That is possible. Not so easy, as I said, but there are a lot of optimization, lot of things to do for that, but it's possible. Using Raman spectra of the organic molecules, biological molecules, it's possible to detect them even at the single molecule. When this type of study we do, not only the sensing but also the chemistry, how they interact, the physics of interaction of those materials with molecules. We have a lot of things going on in our body that's possible. When we take a medicine in our body, there are a lot of nanoparticles, how they interact with the biomolecules in our body. So a lot of things can be studied with the help of this technique. But here I'm talking about use of these materials for sensing or for, we can say, the ultra detection of molecules. Just an example, we can see here. We have nanoparticles on the surface of different sizes, and a molecule comes and interacts on the surface. Based on the spectra, we can see which part is enhanced here, means it is interacting with which part of the molecule. That is also possible to study with the help of this SCRS technique. Other material, as I say, this is semiconductors, because our topic is photocatalysts. So I'm talking about metal and semiconductor and what happens when these two type of materials are combined together. And then when we keep them in under the sunlight, then what happens? So that's why I kept this topic like sustainable and recyclable. So we'll see. The sustainable means how we are using the natural resources for our daily life or for practical applications. So when we have a semiconductor, generally what happens under the effect of influence of light, there is a formation of electron and holes, and when these electron and holes they react with atmospheric oxygen, water molecules, generally they form reactive oxygen species which are highly oxidizing, act as a highly oxidizing agent, and they can oxidize kind of molecules which are coming in contact with them. So generally, when this thing happens in presence of light, we say the photocatalysis. So these materials, semiconductors, generally they are used as a photocatalyst. And these are also used as a sensor, but not like metal nanoparticles, because their sensitivity is very low, but they also show this property. But most of the semiconductors which are being used are like metal oxide or some other semiconductors. Their band gap lies in UV region. So they are UV light activated, but we know if you want to use the sunlight, it has visible light, IR light, and UV. So we need to modify these materials in such a way that we can use more and more sunlight that has more than 50% only IR. So there are possibilities by modifying its property, we can modify their nature, and we can use the entire sunlight even to absorb and modify their properties. So these are not new slides, we have seen already, but the results, there are some results which I would like to show. So generally when we combine these two type of materials, lot of things are there that happens, but overall meaning is that we can absorb more and more light from this naturally available sunlight. And better to see this, overall idea is to separate these electrons and holes, stop the recombination. That is the main thing. In semiconductor, we have this possibility, we can form electrons and holes, and these electrons and holes generally they recombine very fast, and this is one of the drawbacks of this kind of semiconductors. So we modify these materials in such a way that we can stop this recombination and we can make separate those electrons and holes, because those electrons and holes only takes part in oxidation reaction, oxidation or reduction. So there are different ways to separate these electrons and holes. This is one of the way. We have semiconductor, we can use those noble metal nanoparticles, we can use some materials which are very good for electron transporting, like 2D materials, graphene based materials, and nowadays there are a lot of different kind of two-dimensional materials which are acting as a electron transport material. These combinations also very useful for other field. One of the field is antibacterial activity, where again we need these reactive oxygen species, and those species they inactivate bacteria or such kind of biomolecules, even the viruses. So these materials are not only for the photocatalysis or degrading only the organic compounds, but also for the bacteria and viruses. When we combine these two properties, the sensing and degradation, means photocatalysis, then suppose we have some semiconductors with metal. Metal can be in form of nanoparticle. This metal can be in the form of nano thin film. So this is one of the examples where we have some semiconductor coated with noble metal. So when we have noble metals, we can sense it using Raman spectrophotometer, and when we give some light based on the band gap of those semiconductors, they can degrade photocatalystically those compounds, whatever we are sensing, like this is an example of a dye molecule. So when we put some light, those molecules are degraded, the surface becomes clean. Again put some molecules, same molecules, different molecules under the Raman spectrophotometer, and we can have the spectra, so we can sense it. So like that we can recycle this kind of experiments we can do repeatedly many times. So this is one of the beauty of such kind of combinations, metal and semiconductors. Some examples, we have less time actually, so I'm not going too much in detail. Example of silver titania, the similar combination, the metal and semiconductor, and these, here we can see the bigger particles are titania, TiO2, titanium dioxide nanoparticles, even microparticles, and the green color you can see, those are the silver nanoparticles. So the mechanism is the same, how they can absorb the light, they can generate oxidizers. Under Raman spectrophotometer, there is a sensing, and if any molecule comes in contact under the effect of light, they can degrade those molecules. So these materials can be used as a recyclable material. And by using the sunlight, that is one of the natural resources for the light, we can also say these are the sustainable materials. These are the examples. This is antibacterial activity that can be done with the help of these materials. Some other example where we have silver and ZNO nanoparticles, and here what we have done, silver nanoparticles are embedded. Why? Because if these silver nanoparticles are on the surface, they get oxidized in normal atmosphere. So if we embed them within the like zinc oxide or any other semiconductor, microparticle, nanoparticle, they will be safe inside, and their the working efficiency will be for the longer time. So we have tried to manage in such a way that we can have silver nanoparticles on the surface simply, but we can also embed them and we can enhance its working efficiency for a longer time. Some related publications. And something more interesting now, just we had in the last slide silver and zinc oxide nanoparticles, where we had some spherical kind of nanoparticles. Now we have done some new work on zinc oxide tetrapods. You can see a structure with the 4 arms, or we can say the 4 legs. The tetrapod structure, maybe you have seen at the bank of the sea, somewhere if you have gone to the seaside. So these are tetrapod structures. The good thing with this, when we have these kind of structures, because they have 4 legs like your chair, and they are not coming together a lot, and they are not making a bigger particle. What generally happens in case of nanoparticles, agglomeration takes place and its efficiency goes down. So the beauty of this kind of structure, they are not agglomerating like smaller nanoparticles. They have better surface area. They have different edges where nanoparticles can be formed. So we have, this is tetrapod, the pure tetrapods. We have deposited gold nanoparticles on their surface. And this gold deposition is done by photo deposition. Very simple. First, we prepare a tetrapod structure. We keep this tetrapod structure with this aurichlorite or even any other metallic salt. We can use silver nitrate for silver deposition. So when we have aqueous solution, we have silver nanoparticles. We can deposit silver nanoparticles. How? Because in the aqueous solution we have metal ions, means positive ions, and when we irradiate it with like UV light, what happens? The same photocatalyst activity, the zinc oxide generates electrons and holes. So those electrons are captured by those metal ions, positive ions, and forming metal atom. And subsequently, lot of metal atoms are formed and they are deposited on the surface, and finally we anneal at different temperature to form different sizes of the nanoparticles. So it's possible for any kind of noble metal nanoparticles. You can use silver nitrate for silver, aurichlorite for gold, like platinum, copper. So here we have done for the gold. We have also done for silver. So nicely we can see the gold nanoparticles on the surface of these tetrapods. These kind of tetrapod structures are known as three-dimensional nanostructures. So we know zero-dimensional, we know one-dimensional, generally one-dimensional like nanorods, nanowires. Over here, like one-dimensional. Two-dimensional, generally we talk about graphene. Everybody knows about graphene. These are three-dimensional because they are bigger structures. None of the dimensions are within this 1 to 100 nanometer scale. But still they are called three-dimensional nanostructure because somewhere on their surface, somewhere in their structure, there are formation of nanostructures also. Means something of nano size. So that's why they are also called nano. They are three-dimensional but still nano. So these combinations are very different. We have used such combinations for different applications. Here again, I show mainly what we do in our lab. These are the optical properties. We can see here, this is zinc oxide. When we use gold nanoparticles on their surface, the absorption, this is UV visible absorption spectra, you can see the absorption increases. It means due to presence of those gold nanoparticles, its absorption capability is increasing. Even it goes to IR range, near infrared. This is up to 800 nanometer, but it's not the full spectra here, but it goes up to NIR region. It means it's possible to absorb not only UV, that was done by zinc oxide only. Due to presence of these gold nanoparticles, this absorption is increasing up to near infrared. Then other properties, this is photoluminescence, that shows generally the recombination of electrons and holes, which are generally generated when light falls on material. So it shows the recombination rate is decreasing with the after depositing these gold nanoparticles. It means there are more and more number of electrons and holes. Those are participating for further oxidation and reduction. So different kind of materials. We have used dyes, some drugs like ciprofloxacin, a normal drug that generally we use, tetracycline. So different organic molecules have been used, and we have checked the efficiency of these kind of materials. So we prepared different combination with a different concentration of gold nanoparticles with the increasing concentration. So this number shows the time of exposure of the light while depositing these gold nanoparticles. So you can just consider the increasing size of nanoparticles, gold nanoparticles on the surface of this tetrapod structure. So out of 3-4 structures, the one we can see here, the designed as A10, that shows 91, and A15 that shows 96% degradation in case of dye. So we can say that the nanoparticle size, shape even can also be, but we have not worked on the shape. Normally these are forming kind of spherical kind of nanostructures. So we can optimize to have better efficiency and more degradation. So A15 that shows the best. And we did SCRS also. SCRS you can see for different combinations, and at least the one combination shows better the result peaks, means the identification of those organic molecules from sensing point of view. This is the mechanism, the simple mechanism which just I explained earlier, how when gold or silver or any metal nanoparticles like noble metal nanoparticles on the surface, how they behave, how electrons are generated, and then further reactive oxygen species and degradation of particles. And because of presence of gold nanoparticles, there are electromagnetic enhancement that generally enhance the Raman scattering. Generally when a molecule interact with this laser in Raman spectrophotometer, this Raman enhanced only due to presence of gold or silver nanoparticles. And again, that depends on the size. So we have formed different size of gold nanoparticles. Any one of the size that shows the better spectrum. So we can tune the shape and size, and we can enhance the sensitivity. And this work, recently it was published in ACS Journal. Similarly, we also worked on cadmium sulfide nanoflowers, and that also shows very nice results in case of photo degradation as well as photosense. So I have shown only one result, and it is recently published. Last year we worked, and I show you one of the students, Dharma. He worked on that, and he is now going to complete his PhD. This also, I think I showed last time, that these materials are used for other microbes, viruses also. And one more thing I'd like to add, because of these different properties, not only the sunlight, but also they have this tendency, these materials can act as a good antibacterial agent under the dark condition because of these gold or silver kind of nanostructures. Because they have this tendency, if you keep in sunlight, they absorb the light, and later this light can be used as a heat or different kind of radiation that can kill those kind of microbes or viruses. So not only the outdoor but also the indoor conditions, in indoor conditions or dark conditions, they can be. Different applications for solar cell. Here, talking about two-dimensional nanomaterial. Last year, I think I discussed this but not fully, because it was not published that time. What is good thing here? We know graphene. Most of the people know graphene. That is highly conductive. Now, when we introduce this oxygen, simply we have carbon-carbon bond. When we introduce oxygen in liquid, what it does, it interferes the transfer movement of ion. So this introduction of oxygen provides semiconducting. Graphene is fully like metallic, but when we make kind of semiconductor, it can be used like other semiconductor and in different way also. So we prepared graphene oxide by optimizing different conditions. Only what we found that is very different, that is the recyclability. And this recyclability comes under the sunlight. Under the sunlight, because it is visible light active, not UV light active. So directly it can be used in the sunlight, and it has the capability to absorb the sunlight. And what happened? Because it's a two-dimensional materials, its surface area is very, very high. So this kind of materials are used as an adsorbent. Like charcoal, we have learned about the charcoal. Same, these materials are good adsorbent. So we can absorb any kind of molecule because of their good adsorbing property. And just keeping in the sunlight, we can degrade them, because they are also acting as a semiconductor. And these are metal free, there are no any metal. So that's why the beauty of graphene oxide based or any other semiconductor which doesn't have metal, that would be even better, because whenever we use any material of metal, there is a probability of metal leaching. And metal leaching means metal ions. And those ions again act as like antibacterial agent. They can also kill microorganisms in our body. So when we drink water, so this research mainly concern about the wastewater treatment, because we are treating water for the purification. If some traces still remain there and it goes in our body, the photocatalysis process can be done inside, because there are a lot of things that generates these oxyradicals. Not only this sunlight effect, there are other factors also. So if there are metal ions that can behave like that, but if we have some nanomaterials without metal ions, those are better. So these kind of materials are, in case we can say, the recyclable materials and also metal-free materials. So this is something new we have done. And this part is published again, good journal. Similarly, we worked on different material, two-dimensional material, molybdenum disulfide, and this is also behaving the same behavior like graphene oxide, and they recently published. So I'm not going in deep about this material because we have discussed the same property like graphene oxide. Only the thing is, it's a different material, different chemistry, and different activities have been recorded there. But this recyclable adsorbent is part still there. So I mean to say, we have studied in a similar way with some multifunctional activity. So these materials are not only act as a catalyst, but depending on the field where we are using, it can be used. Solar light, radiation, solar energy, gas sensing, different types of like antibacterial, antiviral, and light emitting diode, like LEDs. Learned this in the first lecture. My collaborators, and I would like to thank DB College, Dr. Putti, and the other members of organizing committee, and some agencies has helped me for growing in this research, providing some projects, funding. So, not much. Again, conclusion is the same, that this material can be used as a multidisciplinary research field. Title of this conference, research, just kind of multidisciplinary research. And same material, depending on the requirement. That's it. Thank you. Thank you.
Thank you so much, sir, for comprehensive illustrations and contemporary knowledge. Now the house is open for any questions.